Okay, let's take a look at example 1. So the problem says that in 2016, the population of Florida was about 20.61 million people. In 2000, it was 15.98 million people. Write an exponential growth equation. Okay, so we're going to write an equation that should, if things continue as they have, it should be able to predict the future growth. It should even be able to come up with a value for what previous years' populations would be, right? So we're going to create some kind of function that'll model this growth over time in both directions. Okay, so let's fill in the values that we have. So our equation, y equals ae kt, is has kind of 4 different things to pay attention to. We have the initial value, we have the final value, we have the time period, and we have the growth rate. So let's look at what we have. In 2016, we have a population of 20.61, so that seems like a final value to me. So I'm going to say 20.61 equals the initial value, 15.98, times e to the kt. Now we're looking for a growth rate, which we do not have yet. But we do have a time period. That time period looks like it's covering 16 years. So k times 16. Okay. So once we have this, keeping in mind that e is a constant number, right? It's that 2.7 number. So we've got everything filled out other than one unknown variable. So we should be able to solve for that unknown variable. Okay. So what I'm going to do first is I'm going to divide both sides by 15.98. We'll call that 16k over here. Let's simplify that left side first so I don't have to write all those numbers out over and over. 10.61 over 15.98 is approximately 1 point, I'm going to call that 1.29. Okay, now we use our natural logarithm on both sides. So we say the natural logarithm of 1.29 should equal the natural logarithm of e to the 16k. We'll use one of our logarithm rules, which allows us to pull this exponent down to the front. So we'll get that the natural log of 1.29 equals 16k natural log of e. Well, keep in mind, natural log of e is saying log base e of e. That equals 1. So this whole thing just becomes a 1. And we don't need to have it in the equation anymore. Just multiplying by 1, right? It doesn't really do anything. Oops, should not say, oh, no, it should. My mistake. Okay, so we can get rid of that piece. And then to solve for k, we're just going to divide by 16 on both sides. So natural log of that value divided by 16 should be my growth factor. Okay, so let's do that. Let's go, we'll take this whole thing, natural log of it, quantity by 16. What do they want me to do? Let's change this to that one. F4, and then that needs to get divided by 16. Okay, 0.01, I'm going to call that 0.016. Okay, so if I take that back to my original equation, then I've got 0.016 times, well, I'm going to make it times t, right? Because we just want it to be, want to fill in this equation. So what is our final thing? Our final thing is going to be that our population at any given time going to be equal to that initial population of 15.98 multiplied by E times our K value is 0.016 T. Okay, so let's take that to Desmos and make sure it matches up to the values that it gives. Okay, so if I do y equals 15.98 e to the 0.016 x, let's call it, we should start out at our initial time of 0 years. That stands for, the year 2000 in our problem. In the year 2000, they had 15.98. Let's see if we get that. 0 and 15.98. And then at the year 2016, so we're going to move over by 16 units, we should be at 20.61, hopefully. 16 puts us at 20.6, yeah, 26.64. Okay, that's because I did some rounding. Okay, so that lines up with our 2 points, and now we have a function that not only predicts the future population of Florida, but also should kind of propagate backwards to predict past population. So if we went to like population in 1850, as long as whatever the conditions that influence that particular growth rate were consistent over time, which I probably wouldn't assume they would be, but let's just talk about ideal situations here. As long as the growth rate had kind of the same things that created it over time, then you ought to be able to take this equation and go back to say, okay, this would be population in 1950 would be 7 million, and population in year 2100 should be 80 million. Okay, so that is how we would handle example number 1.